Welcome to This Explainer. Today, we're going to skip all those dry textbook formulas and unpack a really fascinating chapter on proportional reasoning. We're going to discover how it's actually this ultimate hidden survival guide governing literally everything around us, from the breakfast on our tables to the highways we drive on. So let's dive right in and uncover the mathematical framework that keeps our world functioning in perfect balance. Let's kick things off with a highly relatable kitchen crisis. Picture this. You're making breakfast and you suddenly realize a bunch of extra guests are about to walk through the door. Total panic, right? If you need to make a massive batch of idli batter, how do you make absolutely sure it still tastes exactly right? You can't just blindly throw ingredients into a bowl and hope for the best. You need a reliable system. The secret here is maintaining a direct proportional relationship. Specifically, for traditional idli batter, you want to mix exactly 2 cups of rice for every 1 cup of urad dal. We write this out as a 2-to-1 ratio. Whenever 2 or more related quantities change by the exact same factor, well, that's what we call a proportional relationship. It's a brilliant example of complex math hiding right in plain sight in our daily routine. But how do we know for sure that different amounts will actually yield the exact same result? Our chapter introduces us to 2 people, Vishwanath, who uses a 6-to-3 ratio, and Puneet, who uses a 4-to-2 ratio. Are these identical? Let's verify it using the cross-multiplication method. If you multiply Vishwanath's 6 by Puneet's 2, you get 12. And then multiply Vishwanath's 3 by Puneet's 4, and hey, you also get 12. Because those cross products match perfectly, we know for a fact that 2 ratios are proportional. Both of those batches are going to make identical, perfect idlis.
Section 1. Scaling up with maps.
Now, taking this basic concept totally out of the kitchen, have you ever actually stopped to ask yourself how cartographers managed to take thousands of kilometers of rough terrain and literally shrink them down into something that fits right in your hands? They use the exact same proportional reasoning we just used for our breakfast, just scaled up to a massively different level. The crucial trick is how they express this scale using a representative fraction, or RF for short. So for example, if you spot an RF ratio of 1 to 60 log, which is 6 million, tucked in the corner of a map, it means that a distance of just 1 centimeter on that paper perfectly represents 60 log centimeters of actual ground. Let's convert that to make it easier. 60 log centimeters is 60 kilometers. So 1 centimeter equals 60 kilometers. That is proportional reasoning, giving us the superpower to hold an entire subcontinent in our hands. Section 2. Mixing multi-term ratios. So what happens when we need to balance more than 2 ingredients? Say, when we are physically building the cities found on that map. To build heavy-duty structures, construction workers can't just mix 2 things. They rely on multi-term ratios. For high-strength concrete, they use a very specific ratio of 1 to 1.5 to 3 for mixing cement, sand, and gravel. It's the exact same principle as our idli batter, just with a few more moving parts. Let's break down the math to see how this plays out on a real job site. Imagine a site needs exactly 110 units of concrete. How much of each individual ingredient do they need? Well, first, you just add the terms of your ratio together. 1 plus 1.5 plus 3, which gives us 5.5. Next, you take your total required units, 110, and divide it by that sum of 5.5. That gives you 20. And that 20, that is your magic multiplier. Finally, you simply scale every single ingredient up by 20 times. So that means 20 units of cement, 30 units of sand, and 60 units of gravel. Perfectly balanced, structurally sound concrete.
Section 3. The slice of the pie. Let's step away from the construction site and into a school building to see how proportions help us visualize raw data. If we divide student grades into a multi-term ratio of 6 to 5 to 4 to 3 to 2, we can easily convert those abstract numbers into the angles of a pie chart. We do this by taking the proportional slice of a 360-degree whole. Take grade 8, for instance. It represents 6 parts out of the total 20 parts, or 30%. If you multiply that fraction by 360 degrees, you get a perfect 108 degrees slice. Proportions essentially allow us to translate messy, raw data into really clean, instantly understandable graphics.
Section 4. Direct versus inverse proportions. Up until now, absolutely everything we've looked at has scaled up together. More rice meant more dal. More map distance meant more real distance. But prepare yourself for the big flip. What if getting more of something actually gives you less of something else? Think about a road trip from Lucknow to Canberra. As your speed increases, say going from 5 to 15 to 30 and all the way up to 60 kilometers per hour, your travel time totally plummets, dropping from 18 long hours down to just an hour and a half.
We call this an inverse proportion. The quantities are still changing by the same factor, but they're moving in completely opposite directions.
And here is the beautiful, elegantly simple mathematical formula that governs this whole inverse relationship. X times y equals k, where k represents a constant. If you multiply those opposing numbers from our road trip, like a speed of 30 and a time of 3, or a speed of 60 and a time of 1.5, they're always going to equal the exact same constant number. In this specific scenario, that constant is 90, representing the fixed 90-kilometer physical distance between the two cities. This inverse concept isn't just a quirk of road trips. It is literally everywhere. The exact same rule dictates that adding more pumps fills a water tank in a fraction of the time. Or if 20 extra students suddenly enroll in a school, the existing food provisions are going to drain a lot quicker. And hiring more painters drastically slashes the days needed to finish painting a wall. In all these cases, as one variable goes up, the other simply must proportionately go down to maintain that constant K, whether that happens to be the volume of the tank, the total amount of food, or the total size of the wall. I want to leave you with one final puzzle straight from our chapter to test your brand new proportional superpowers. If 3 workers can paint a fence in 4 days and your team gets bigger by exactly 1 person, how much time do you actually get back? Remember the inverse rule and think about the constant amount of total work required. I highly recommend grabbing a piece of paper and working this one out for yourself. Thank you so much for joining me on this explainer, and keep looking for that hidden math everywhere around you.